Hi, this is Dr. Kahn with Chapter 3.1 and 3.2, talking about rocks, the materials of the solid earth. Here are the learning objectives for 3.1 and 3.2. 3.1 talks about the earth as a system. It lays out the basic steps of the rock cycle. Note the vocabulary here. The words are also included in the diagram Smart Figure 3.1. If you download the copy of this PowerPoint, you can click on that Smart Figure link, and it links to a video that describes the steps of the rock cycle in more detail. You can also access the Smart Figure by using the QR code or web address that's printed in the online version of your textbook. The full cycle does not always take place because sometimes shortcuts are taken or interruptions. So the cycle does not indicate that every step is hit along the way. Section 3.2 is on igneous rocks, rocks that are formed by molten magma. As magma cools and crystallizes, it forms into igneous rock. Therefore, any rock, sedimentary, igneous, or metamorphic, that melts will then cool and harden and turn into a new igneous rock. Depending on the depth that the rock forms, our crystal sizes will be different. Crystal size is an indication of how quickly a rock cools. Rocks that are buried deep beneath the earth will cool more slowly, and larger crystals will have an opportunity to form. Rocks that form very quickly when they're cooling at or near the surface will form very small or microscopic crystals, or sometimes they'll cool so quickly that no crystals can form at all. Igneous rock compositions are important to understand and help identify which igneous rock you're looking at. Igneous rocks are mainly composed of what are called silicate minerals. Light-colored rocks that are high in silicates are called granitic or felsic. Those two words are synonyms, and you might see either one. They both mean the same thing. Granitic or felsic means high in silica and light in color. Basaltic or mafic compositions are richer in dark silicate minerals. They're darker in color. They also give us an indication of where or how this particular igneous rock formed. Smart Figure 3.4 is important. If you want to click on that, again, in the PowerPoint or in your online e-text, there's a video that corresponds with this chart. This chart is important to understand, and I really recommend even pausing this video and taking a minute to acclimate yourself to what it is that you're looking at. Along the top, we see our compositions, granitic, andesitic, which means an intermediate somewhere between granitic and basaltic, are basaltic compositions, and then ultramafic. If the rock that forms from this composition is granitic or felsic, the resulting coarse-grained rock would be granite. The same material, if it's fine-grained, will cool into the rock rhyolite. The difference between granite and rhyolite is the crystal size. Remember that coarse-grained crystals are large crystals. Those form deep underground with a slow rate of cooling. Therefore, if you take magma that's granitic, felsic, high in silica, and you let it cool slowly underground, you'll form large crystals, and the resulting rock will be granite. But the same composition magma, if it extrudes from a volcano or it cools close to the surface where it can cool rapidly, the same composition will give us a different rock with smaller crystals or fine-grained, and it will be called rhyolite. The same principle applies for each of these columns of rocks, and it gives us a basis for understanding and identifying these different types of rocks. Texture, shape, and size and arrangement of minerals that make up a rock tell us something about its history. Again, fine-grained or small crystals tell us that there was a fast rate of cooling, meaning that the rock formed at or near the surface. Coarse-grained indicates slow cooling, meaning the rock was formed somewhere deep underground where it had enough time to form large crystals. Porphyritic is a vocabulary term that means it has two crystal sizes, indicating two different rates of cooling. To understand this better, think about the fact that maybe deep underground, large crystals began to form, but then the magma was erupted out to the surface, so the remaining liquid cooled quickly and formed small or microscopic crystals. Therefore, the resulting rock would have both the large crystals that began to form underground and a small matrix of crystals that cooled closer to or above ground. The next texture is glassy. Glass means no crystals. So this type of rock cooled very quickly. This would be an extrusive rock that came out of a volcano, for example, and cooled so quickly that it did not have time to form crystals. Vesicular is a texture of rock that contains lots of holes because gas bubbles existed in this frothy magma, or frothy lava, I should say, because it has extruded or come out of a volcano. So this is very frothy, gas-rich lava that when it cools and hardens, leaves the space or voids behind where the gas bubbles were. Pyroclastic is the last texture. It's fragments. Sometimes these fragments are cemented together, and it's produced by volcanic fragments that are being shot into the air and welded together. An example of each of these rock textures is provided in your book, but also available as a smart figure video that walks you through the different types of textures. The main focus of our igneous rock identification is going to be with granitic rocks, andesitic rocks, and basaltic rocks. These are the three types of categories of rocks that you'll find in your rock samples from your lab kit. Your felsic rocks will be composed of lighter colored silicates like quartz and feldspar. Common rocks are granite, rhyolite, and obsidian. The andesitic rocks are a mixture of felsic and mafic composition, so you'll see some light colored minerals and some dark colored minerals. Basaltic rocks are composed of dark colored silicates and therefore will be the darkest of your samples, and some common examples include basalt and gabbro. The difference between the rocks listed here is likely just the cooling rate. In other words, our felsic rocks that cool slowly will form large crystals, that's granite. Rhyolite, smaller crystals because it came out of a volcano cooled at or near the surface. And obsidian, which cooled so quickly that it turned to glass. Our basaltic rocks, basalt would be the cooling rate that's quick, indicating that there was some volcanic eruption. Gabbro, same composition, but it cooled very slowly, so we have large dark crystals. The classification chart here for 3.8 is also worth viewing and viewing as a smart figure. They'll go over the mineral composition chart. On the other axis is texture. And so again, when we have a granitic texture, this is felsic, high in silica, light colored minerals that are coarse grained because they cooled slowly. The intersection of these two indicate that we would have granite as a result of this composition and this cooling rate or texture. Note that there is one sort of exception on this chart in terms of color. We say that granitic is light in color. It has light colored minerals, but when it cools very quickly, too quickly to form crystals, we get obsidian. Obsidian is a dark colored rock, glassy type of rock. And although it is dark, it is considered granitic or felsic due to its high silica content. The fact that it cooled very quickly just makes it glassy and look dark. How igneous rocks formed is explained by Bowen's reaction series. It shows the order in which minerals crystallize in terms of rising temperatures or falling temperatures. Take a minute to look at figure 3.13, Bowen's reaction series. As rocks are cooling, they start at high temperatures. As they start cooling, these are the minerals that will start to form. So olivine is a very mafic mineral. That's one of the first minerals that will form out of magma as it starts cooling. And at the other end of the spectrum, we have quartz, which is the last to cool out of a magma, cooling at the lowest temperatures. We can also run this in the other direction when we think about rock that's melting. Rock that's being heated up and melting will have quartz melting first and olivine melting last. This set of reactions really helps us to understand how a rock came to be and formed, and what minerals we might expect when some of, but not all, the minerals begin to crystallize out of a magma chamber. That is the end of 3.1 and 3.2. Thanks for listening.